All right, let's go and review some things we talked about in our last lesson. We were talking about our third major conic section called the ellipse. And we said the ellipse is different from the last two conics in a number of different ways. First of all, the eccentricity of an ellipse is different from the other two. A circle's eccentricity is always equal to 0, and in a parabola's eccentricity is always equal to 1. But the ellipse has varying eccentricities, right? It could be a number of different things as long as the value is between 0 and 1. So it's in between an eccentricity of the other two. As the eccentricity approaches 0, the ellipse approaches becoming a... As the eccentricity approaches 0, what happens to the ellipse? It looks closer and closer to an actual circle. That would be kind of like the Earth's elliptical orbit. It's very nearly circular. Eccentricity closer to 0. And then as the eccentricity approaches 1, what happens to the ellipse? It gets skinnier and would eventually, if you had a 1, it would actually be a straight line, right? At that point, it wouldn't become a parabola, it would become a straight line. For the conic form, we said what? We can see an equation and know we've got a circle when we see what?
X and y squared.
Yeah. X squared plus y squared, blah, 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 right? We know we've got a parabola when we see what?
X squared or y squared.
X squared or y squared, blah, 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 but not both. What about the ellipse? What are we going to see with the ellipse? We're going to end up seeing something x squared plus something else, specifically y squared. So with the circle, they had to have the same numbers, so we could divide it out and get a 1. With the ellipse, they're going to be different numbers, so if we divide it away something, we get different values. What is the elliptical form we're going to try for our equations? Class?
X minus y squared, or do you want
the elliptical form?
Okay, x squared over a squared plus y squared over b squared equals 1.
There we go. We want to end up getting the x squared and y squared by themselves, but because they have to have different numbers, if you set the equation equal to 1, they're going to have different numbers underneath. Now with the ellipse, we said it's a distorted circle, so it's either long or it's tall, one or the other. If it's long, we would say that the x-axis is the major axis, because it's technically symmetric in both directions, isn't it? So we say x-axis is the major axis, and the ends of the major axis are called the vertices. It could be this way. Let's go with the tall one this time. Vertices. And the midpoint of the major axis is the center, right? Now, if we measure from center to one vertex or center to the other vertex, obviously they're equal because the midpoint, center is the midpoint. How would we algebraically represent that length from center to vertex? It's represented by the little letter A. Little a. So remember, the entire major axis would be represented 2a, because each piece is a. Perpendicular to the major axis, running through the center, we have the minor axis, and each side of the minor axis is represented b, so that the total length of the minor axis is 2b. And then there's two really important points inside the ellipse called the focal points, or the, what's the plural of focus? Foci, right? We have two foci. And in fact, the foci are what really define the ellipse. Let's pause for a moment. What is an ellipse?
It's a locus of points, and the sum of their distance is equal from the 2 points.
Locus of points is constant sum.
There we go. You mentioned the sum, but it's constant. That's the key word, the constant sum of those distances. So the distance of, in our ellipse, we've got focal point here, focal point here. All right, you take this point here, measure D1 and D2. If you add those two together, take this point. Well, it's got a D1 and a D2. And if you add these two distances, you're going to get the same thing you got when you added those two in a true ellipse. Now, probably the foci are actually a little further out, but you get the idea, right, on that. So those foci are really important. The foci always lie where?
On the major axis.
On the major axis. And if you were to measure from center to one focus or center to the other focus, that focal length is represented by the letter
C.
C. How do we find C, the focal length?
C equals square root of A squared plus B squared. Or no.
Help?
Minus B squared.
A squared minus B squared. So we're going to take the denominators that we formed by setting the equation equal to 1, subtract, and take the square root of those squares. That gives us the focal length. And for the eccentricity, we said we could calculate eccentricity by taking what ratio?
C over A.
C over A. The focal length over the half major axis length, where the focal length is always going to be smaller. By the way, for the parabola, how do we calculate eccentricity? I know it was always equal to 1, but how would we calculate it? It's based on the locus of a parabola. The distance of any point to the focus compared with distance to the directrix. You can tell it's poorly drawn because they don't look equal. But on a true parabola, distance to focus of any point on this curve is always the same as that same point's distance to the directrix. So for parabola, d sub f to d sub dd prime is your eccentricity. It just happens to always equal 1. Here, it's not always equal to 1. It's just always between 0 and 1. There are also, just like in a parabola, there is a focal chord that's perpendicular to the axis of symmetry. So in an ellipse, there are focal chords through the foci perpendicular to the major axis. These are called latera recta, right? Each one is a latus rectum, 2 latera recta, and we use those to help get a really pretty good shape, I would say, for our ellipses, right? We're able to graph fairly accurately with those added points. We said that the basic form of the ellipse is x squared over a squared plus y squared over b squared equals 1. Again, the key is get it equal to 1. But we said this would only be true if the center of the ellipse is at 0, 0. If the center were to move, I would have to change the form just a little bit. Now, what's the rule about a squared and b squared?
A squared is always the larger.
A squared is always the bigger one. So if the big number is down here, then it is the a squared. If this is the big number, then that's b squared, and that's a squared, right? So that'll change. And the significance of that is, whichever one it has the a squared is our major axis. So think of it this way. The bigger this number, the smaller that number. So whichever number is bigger, the other one gets to be major, is another way to think of that, I suppose. All right, let's go ahead and graph one of these. Go ahead and set up a Cartesian plane on your graph paper. And then we'll get into our new material. But let's start by taking just a few moments to graph this ellipse. Definitely can't be a parabola, it's got 2 squares. So 9th graders usually come in after all of this. You actually get to see what it looks like when it's being done. If you care. We're going to get your homework done. Probably better use of your time. did we get this equation when we set it equal to 1?
Yes.
All right, let's take a look here. Where's the center of our ellipse?
4,
Or
2.
2.
Which axis is going to
Mr. Zadowski,
be? Yes, ma'am.
do you have Charles Gibbs in your class?
Yes, ma'am.
Pastor Adam would like to see him in his office.
I'll send him down.
Thanks so much.
Yes, ma'am. We're going to edit that out. All right, replay. All right, let's take a look at this. And where's the center of our ellipse, class?
4, 2.
4, 2. Which axis is the major axis?
Y.
How do we know?
Because it's bigger.
Bigger number. Now, it's not a real y-axis, right? We're going to make a prime y-axis, but the y-axis nonetheless. The major axis is going to be how long?
12.
12 total units, 6 in each direction. Now, here's where it gets fun. What about the minor axis?
6.9.
That's fine.
Yeah, it's going to be square root of 12 each, or you could say 2 times the square root of 3 each, right? So that means it would be 4 times the square root of 3 total, which is just annoying. It is about 6.9 total. 2 square root of 3, which is about, what, 3.4 or 3.5 each?
Yeah.
2 times the square root of 3, yeah, that'd be about 3.5. right? 3.46 or 3.47.
3.46.
Okay. Focal length ends up being here initially the square root of 24. We know that's going to be almost 5. Maybe what, 4.8?
4.9.
Yeah, 4.9.
4.9. Okay. And then the half ladder erecta lengths end up being exactly 2. B squared over A. That's something I forgot to ask earlier, actually, when I was reviewing other things. Remember, each half of the lattice rectum, B squared over A, the whole thing 2B squared over A. Here's the B squared, A is 6, so a nice even 2. So should have come over to 4, 2 here in the first quadrant. Lightly draw yourself a y prime axis. Along the y-axis, go up and down 6. So that goes all the way to the top of my Cartesian plane. Go outward about 3.5. Go 4.9, so almost 5 to the foci. And then from there go out exactly 2 in each direction to the ends of the ladder erecta. And then again, from your vertices, man, it's hard not having a guideline to be approaching. I think right about there. And I have to go through that. I have to go through that focal point or that end of the lattice rectum, so I can't go around it. Oh, lovely. All right, so let's try this again. So we're going to curve through and just keep approaching until we get right there. And retrace that. Right about there. I'm so used to having a line I can come into, and I don't have that right now because of the half. Whose idea was this? Who comes up with these problems? Oh, jerk. All right, and so something like that should be our ellipse. How do we do?
I actually went out 6.9 for my X.
Oh,
Yeah, mine
okay.
Wait, I did something wrong too, I just realized.
Okay, questions, comments?
Somehow I switched the vertex. I went over 2 and
You went 2, 4 instead of 4, 2. Okay. Gotcha. I was like, wait, yours comes over the y-axis
Wait
there.
a minute.
Yeah, okay. Questions? All right, well, we see the translated center, but you won't necessarily see that in the conic form. So the next section, you notice, going from conic to elliptical form. Conic to elliptical form. Conic to elliptical form. I mentioned at the outset, pretty early on, that conic form, remember, is going to have a different coefficient for the x squared than for the y squared. So for instance, a 9x squared plus 4y squared minus 18x positive 16y negative 11 equals 0. I know it's an ellipse. Why? Because like the circle, you have x squared and y squared. They're both positive, but they have different coefficients. That tells me ellipse. Step number 1 is to group x's and y's and kick out the constant. Group x's and y's and kick out the constant. So I'm going to put the 9x squared and the negative 18x together. I'm going to positive 4y squared and the positive 16y together. And we're going to kick the 11 out. Now, by now, we've done enough of these to know at some point we're going to make a PST. At some point, we're going to complete the square. But you can't complete the square without a 1, at least not easily, and I'm lazy. So we've got to have a 1 here, and we've got to have a 1 here to complete the square. So the next step is to factor out common factors from each group, or factor out the common factor from each group. This group has a common factor, and this group has a common factor. Factor out the common factor from each group. Now here we can see the common factor is 9, but this will sound familiar from the parabola. Even if the 9 weren't common, I'm still going to have to pull it out. Even if this is a 15, you have to pull out the coefficient because you have to get a 1. So we say common factor. Well, it may or may not be common, but whatever's in front of that x squared, you have got to pull out. Fortunately, it pulls out easily to get x squared negative 2x. I'm going to leave just a little bit of space. We do the same thing with the next thing. The common factor is a positive 4. Even if it weren't common, I still have to pull out the 4, though. That fortunately does work out common. I'm left with
Yeah.
Y squared plus 4y. Just the coefficient, not the x and not the y. So I'm not pulling out a 9x, just a 9. Not pulling out a 4y, just a 4, because I need the squares to start my PSTs. And then leave a little space, equals 11. So factor out I guess I said factor out the common factor. A better way would be factor out the coefficients of the squares in each case. Factor out the coefficients of the squares would be a better way to phrase that. Step number 3, complete the square. The whole reason we did the factoring was so we could complete the square. And of course, to complete the square, 2 steps, class. Half and a square. Again?
Half and square.
Half and a square. So when we half and a square here, we get a
1.
and here we get a
4.
always positive, right, when we square. Now here's the deal. They look like a 1 and a 4, but they're not. They lie to you. It's like a politician. Looks like a 1. But because it's grouped in parentheses with a 9 preceding, it's not worth 1. It's worth 9. This looks like a 4, but it's not worth 4. It's worth 16. It lies to you. It's a politician. It's like Bernie Sanders. He looks like he's the advocate for the poor man, yet he owns 3 houses. Okay? So anyway, going politics here. All right, so since this is really worth 9, and since this is really worth 16, what we put on one side, we have to put on the other. But I don't put a 1 and a 4. I put a 9 and a 16. Does that make sense? Politics aside. All right. But now maybe you'll remember. All right. Watch out for politicians as you complete the square. All right. So we have to also, as I said, complete the square and add to the other side. But you might put a little asterisk where it says add to the other side, because you got to watch out for what you're actually adding to the other side. What are you really going to add? Maybe something about multiply in there. I'm not sure a good way to phrase it, but make sure what you add to the other side is really the value. Add the real value to the other side. All right? Not the number, but the value. Maybe that's a good way to put it. We should have thought that through ahead of time. Don't add the number, add the value to the other side. The next step you probably would assume on your own. The whole reason we completed the square class was so we could get the binomial squared. So get the binomial squares, and while we're at it, we'll condense the constants to a single value. 36. So binomial squared and condense constants. I'm going to put that in my notes now. I've been teaching this for 12 years, and I never thought of a good way to phrase it. Add values, not numbers, to the other side. See here? You guys just inspire me. Look at that.
Happy.
I appreciate it. Tell you what, I will give you, since your inspiration helped to drive success for me on my YouTube channel, I will give you a piece of all of my proceeds for this year.
0.
It's a 0. I'll give you a piece of 0. All right. Just for that, maybe someone's like, ooh, I'll mail in cash. You have the address, the information. You can find it on my YouTube channel. So Grace Christian School's website is there. You can find the school's great mailing address. Just care of Robert Nadasky and mail a check, and I will share with my seniors who inspire me to new heights. All right. Or 9th graders in the back in study hall could also give me donations, which I would share with seniors who inspire me. Donations are always accepted.
Where will we get this money to donate?
That's not. I don't ask questions where the money came from. I don't want to know about your dealings, but I take cash. All right. Oh, we have cash.
Oh,
All right.
yes.
Now I have to have enough to actually split with the seniors here. Are you? I only have 2. How am I supposed to split this among 3 people? Maybe somebody else will donate $1 at the end of the hour and we can split $1 a piece. All right. My unashamed plea for cash. All right. The next step should be obvious. Set it equal to 1. Set it equal to 1. Because at this point, we're like, hey, I've seen this form before. We've started you here before. We just never started you previously. And so what's my end result when we got it in the elliptical form here?
X minus 1 squared plus y plus 2 squared
There we go. And so the center of the ellipse is at 1, -2. So if I were to graph, I'll just go throw a quick sketch up here. 1, -2. The major axis is going to be the y-axis again. So this is going to be a y double prime axis. We're going to go along the y-axis, up and down.
Yeah.
Well, total 6.
Well,
3.
Up and down 3, right? So there's the vertices here. Each side of the minor axis,
2.
just 2 for a total of 4 for its total length. Focal length, square root of 5,
So
2.2. All right, so a little beyond the 2's. And then each side of the latera recta, 4/3. So 1 1/3-ish. And there we go, out in each direction. And so we get an ellipse that looks something like that. And there we go. Questions on this? Run through the steps again very quickly. You group your x's and y's and kick out your constant. Pull out the coefficients of the squared variables. And then you're able to complete the square. But when you complete the square, add the value of those completed squares to the other side. Get your binomial squares, condense the constants, set it equal to 1, and we're good to go. Write this down if you would please now. X squared plus 9y squared minus 6x plus 36y minus 36 equals 0. X squared plus 9y squared minus 6x plus 36y minus 36 equals 0. All right. First things first, what we got to do?
Group X is y.
All right, so what do I write, Jamie?
X squared, minus 6y, 6x, 9y squared, 36y, and equal to 36.
All right, then what, Quentin?
Factor out the constant.
Factor out the coefficients of the squares. So here and here, what's that number that's got to be factored out?
9.
Technically a 1, do you have to write it? I don't know. Here, what do we factor?
9.
9, definitely write that. No question there. What do I put inside the parentheses for now, Quentin?
X minus 6x.
Well, x squared minus 6x.
And y squared plus 4y.
All right. What do we put in the parentheses to complete the squares now, Jamie?
Plus a 9 and a 4.
What do I add to the other side, Quentin?
A 9 and a 36.
A 9 and a 36. So now I should take both of my PSTs, turn them into binomial squares. So Jamie?
X minus 3 squares plus 9 times y plus 2 squares equals, is it A1?
All right, then what, Quentin?
Say 1. Well, divide everything by 81.
Divide everything by 81. Of course, that'll be over 81. Here, if I divide by 81, I'm going to cancel to get a 9 in the bottom. And then, of course, over here, I just get equal to.
9.
All right. You can use the graph grid that you used for your earlier ellipse. What is my center point going to be here?
3 negative 2.
3 negative 2. Oh, that's right on top of the last ellipse. I'll start over for your benefit. You could probably work around your ellipse, but I've got 2 of them already on here, and they're getting in the way of each other. Having too many superstars on the same NBA team. It doesn't always work out so well. Or you get the Pacers and have no superstars on your team. That doesn't work out well either. Get a good draft pick though. All right, so we said we're going to put the center at 3, -2. Which axis winds up being major? X. So we'll do an x prime axis. How big is the major axis going to be? 18 units long. Now, not 18 in each direction, just 9, but 3, 6, 7, 8, 9. I'm kind of estimating at this point because I didn't set up my graph grid to give me room to do all of that. A little unfortunate. How about the minor axis?
6.
Just 6, 3 in each direction. Not careful, it's going to look an awful lot like a football. We want it to look more like a surfboard. All right. Let's see here. Focal length.
Square root of 72.
Square root of 72. 6 times the square root of 2 ends up giving us what?
8.4.
8.4, 8.5. So 8.5 in each direction. Notice where the foci are. Very close to the vertices. So we're going to have a very high eccentricity here, but it still doesn't look like, it's still not going to look like a straight line, even with a high eccentricity. But it's getting there, it's closer. Each side of the lattice, or the latera recta, end up being what?
1.
Exactly 1. So up and down 1. And again, just kind of estimating and eyeballing here because graph grid, you know. And this is fun. So start of the vertex. And try not to start straight lining too soon. That's easier said than done. Who came up with this one? Something like that, and it's one of those times you're thankful for an eraser, and it's why we use pencil. And sometimes stupid people who provide these give you really long, annoying ellipses, and that's not exemplary by any means, minus a point. All right, but I'm lazy, we're gonna leave it like that and move on. The main thing's the algebra, frankly, but questions? You got it?
Mm-hmm.
Page 245 in your textbooks. Page 245 in your textbooks. And let's take a look at letter C. Letter C.
Which?
Oh, sorry, number 10. Number 10, letter C. I skipped right over the number 10 part. Page 245, number 10C. That's actually what's in the notes. Help to read those. And we got a 25x squared plus a 4y squared equals 40y. And if you're not careful, you'll miss the existence of that little y. You'll say, oh, divide everything by 40. No. What do we need to do?
Oh.
Everything by 40y.
Mm.
Move the 40y over as a negative.
Set it equal to 0. Now here, I could already make this a 25x minus 0 squared if I wanted to, right? That's not really much of an issue. Here's the only real place we need to address. We need to factor out a
4.
which will leave 4, which will leave us with in parentheses, which is going to complete with a 25, but on the other side, what do I add to the 0? A 100. This y squared minus 10y plus 25 could be rewritten All right, so when we set it equal to 1, we need to divide everything by 100. So x minus 0 squared, or just x squared, nothing wrong with x squared, over 4, because I'm dividing by the 100, plus y minus 5 squared over 25 as I divide by the 100 equals 1. Questions on that one? It's sneaky. It looks like a really easy one there on 10C, and all of a sudden, oh, that y though kind of messes some things up. Quick analysis here. By the way, I meant to find the eccentricity on this last one. Pause here. Sorry for the scatteredness. We said the focal length here was 8.5, right? 6 times the square root of 2 to be exact. And then each side of the lattice rectum was, or each side of the major axis was 9. So 6 times the square root of 2 divided by 9.
0.9444.
Whew. 0.94. Yeah, I don't like high eccentricities. They're annoying to graph. This one's going to be kind of annoying also. Where's the center? 0, 5. Which axis is major?
Y.
Y-axis. Each side of the major axis.
10. I'm going 5.
5 each, right? So once again, I'm going to the limits of my Cartesian plane here, though not exceeding like last time. Each side of the minor axis. 2. Focal length ends up being the square root of 21, which 4.6. By the way, divide that by 5 real quick.
0.92.
Just can't escape. This one's just about as bad. Almost the same eccentricity. It's going to be another miserable graph. What about the what about the length of each side of the latera recta? 4/5 or 0.8. So not quite all the way to a 1, but pretty close. And finish up this graph real quick and then we'll call that good. Now it doesn't look quite as bad as the last one, so I still like this one better, but maybe because it's smaller. Similar eccentricity, but a lot smaller. Questions on this? All right, homework for this evening, page 245. I want you to do number 10E and 10G. Numbers 10E and 10G on page 245. We'll take a look at those tomorrow. Planning to wrap up the ellipse in our next lesson tomorrow. Have a wonderful rest of your day, and you are dismissed.